All right. Questions about anything before we carry along? No questions about garbage collection at the moment? All right, locality of reference then be our next item. All right, so there are two high-level types. For this concept, one is spatial locality, and the other is temporal locality. Spatial will have a subcategory of sequential locality of reference. Essentially, these are just patterns of access within the system. Based upon these patterns, various techniques or approaches are taken to leverage these paradigms. Paradigm is not the word I'm looking for, but I'll try to remember what the word is I'm looking for later. Okay. Not that I can spell paradigm anyways. Okay, all right. So spatial locality. Overall, locality of reference has to do with resource utilization. With spatial locality, a resource that is close to another resource that was just used has a higher probability of being used used soon than a resource that is further away. Let's see. So do a little code example here. Of course, ignore the capitalization of things. Okay, so all three of these local variables at the moment are just stack variables. So they're all close together in space, plus I also being a stack variable, since we defined inside our for loop. I gotta fix those kids. All right. So what happens when this program's running, right? When we're in the loop, and let's make this a little bigger. Why not? While we're busy doing work in this loop, we have two variables that are being used, both of which are inside the stack frame. And let's say we have some sort of global variable, right? Global, whatever, current time, sort of thing. Static variable. Which are in actually different locations of memory. Static variables have an address space that's close to the global space, and of course that syntax is C++, but it's just for the purpose or the intent. So while we're busy in the loop, we're going to be using I and sum over and over again. Other variables that are also close in memory, X and name, are things that we want to go ahead and bring in all together at the same time, where our expectation is we're likely to use things that are close together than using things that are not close together. So when, right, so let me step back and talk about program execution. In order for our code to be executed, first need to read it off disk. And load it into memory. In the process of executing instructions, we'll need to set up the memory tables that track where the variables actually are, all that good stuff. All right, the symbol tables. Where the variables are stored. These variables can't do anything just sitting in RAM. Will need to be fed into the CPU. Right, so the CPU has multiple areas of memory. We have L1 through L3 cache. So we have the system registers and other areas on the CPU itself. Right, so in order for the value I to evaluate the I++ operation, the operation does not happen on the stack where I is being stored, but rather in a register on the CPU. Same story with sum. We want to add value of I to sum. We'll have to get that into CPU. Okay, so loading up the variables or loading up any area of memory, variables or any area of memory such that we'll hand it off to the CPU tends to be grabbing more than just a single variable at a time. what will often happen is we get to the first variable we need, grab a page's worth of memory and load that into the CPU. So the variables that are near the first variable that's being loaded, are often also grabbed. Let's see, what's our current? Good old Newegg. Let's see, here we go. Got the caches right here. These caches are getting bigger and bigger. 25, it's an unusual number. Anyways, L3 cache, L2 cache. How much is this processor? $400? Wow. This has gotten substantially larger since last semester when we were looking at CPUs. Let's see if we can get to the specs of the L1 in here. Not. All right, where's the cache? It's funny how they don't. L1 cache is typically measured in kilobytes. It might be 256, 512, could be megabyte, as big as these caches are. And so what happens is, as we load things from RAM, those bits of memory are going to be fed into the CPU. The CPU is also going to hold on to the data so that it doesn't have to go all the way to the RAM to get the values of things before we process them, because the further we have to go, the longer it takes things to get the job done. It's kind of like if you need a cup of sugar, you don't go to the store and you buy a cup, you go and you buy a bag of sugar, and that bag of sugar is probably 4, 8, 12 cups, whatever it is. And you bring the whole thing home, and then the next time you need a cup of sugar, you just go back to that same bag. Same idea with how we're managing our memory. We go and grab a larger unit of data and then stuff it all into the cache and then start processing. So when we grabbed I or some or those other variables, we might have grabbed the whole suite of stack variables that were there on that stack frame and then push them into the processor. So when we started going to the other variables that we were working on, there's a greater probability that it's already in one of these caches, which means the code's going to process a little bit faster and the next time that it needs those variables because it's already been loaded up in the cache. And this is like one of the reasons why a lot of programs take a good while to load up because they got to go get all the resources together, pull them up, and then decide which resources we want in memory, and then start running various applications. And also, sometimes you'll see like you do a certain operation. The first time you do the operation, it takes a noticeable measurement of time or amount of time. And then the second time you do it, it's much faster because it's gone ahead and remembered things, kept things around in memory, so that our subsequent operations are quicker because it's remembered them. Right. I have to get to the Intel's real spec document to see what our L1 cache is, but whatever it is, it's going to be a lot smaller than 12 megabytes. All right, so by grabbing, and they're nearby. Cookies are, well, cookies have multiple uses, right? You got your tracking cookies, you got your your login cookies, so it remembers your like at least your username. And so you go to a website and it auto-populates our usernames because it pulled that data from a cookie. Right. It might also have a login token that it's a persistent in your machine, so that you come back to the website later and you're already logged in because it's got that cookie that it's pushing out there. Temporary internet files would be more relevant, where it's restoring images and cascading style sheets and JavaScript and various other things that we've downloaded from. Right. If we go look at right, there's a bunch of JS that's come along, right? The API is Google's. Let's see, let's do refresh here. Network. This will tell us what's come from. Interesting. Didn't bother telling me a bunch of. I was expecting. All right, let's go to a different website. Let's go to Yahoo. All right, let's go to Yahoo Finance. Why not? It's gonna have a bunch of stuff. Right, all kinds of good stuff down here. Remember, was a 302 means it came from the cache or not. Still going, still going. All right, so I don't know if I've been on Yahoo Finance on this laptop or not before, but let's see, we had 467 requests and 5.3 megabytes transferred. So if we do a refresh, hopefully that's gonna be a lot smaller because it's gonna pull more of these things from cache on the second hit. All right, still going, making more requests than the first time. Good old ads. You can see the second time we made the request, it's only 1.6 megabytes of data was transferred. See, there's a lot less activity going on here in my little waterfall chart and all the various threads it's running. There we go. Size is that gives our cache. There we go, cache. All right, so memory cache versus disk cache. So it's a lot faster to load up this memory cache than it would be things with disk cache, and of course it's gonna be a lot slower to load up these things that were not stored on my machine in any shape or form. All right, so caching in general is one of the strategies that's been developed because of locality reference, and the various types of locality reference patterns will help drive what our cache caching logic should be to help support our objective. And the objective is, as it often is in data structures, is to make things faster. And right, just like this code, instead of being a loop, turn that into a function that just does the calculation. It's gonna be a lot faster than going through it step by step. All right, so the other spatial locality of reference is sequential locality, where when we have a list of items, such as an array or program instructions, we very often evaluate those in order. The first and the second, followed by the third, etc. So if we're working with an array, and want to look at a given element, it's likely elements that are near it also be loaded up into other areas of memory. Right, and we're talking about L1 to L3 caches as those areas of memory. With program instructions, what we can do with the CPU is do some read ahead and some pre-processing the next instructions. Right, so the common computer architecture. Let's see, I'm gonna go. Yeah, I'm not sure I can spell von Neumann correctly, so let's go grab von Neumann. Error. Right, which is fetch, execute, fetch. In a nutshell. All right, so we read instruction 1, execute. Instruction 1, then fetch. Instruction 2, and repeat. All right, so some CPUs have a pattern called pipelining. Just grab a link for that. Pipelining, that's pretty good. That's good. Whereas an instruction is working its way through the CPU, we'll go ahead and start evaluating the next instruction. Evaluating next instruction as the previous instruction is working its way through. Right? So some instructions, right? So some machine level instructions will take more than one clock cycle to get through the CPU and out the other side. So instead of parts, the CPU remaining idle while the first instruction is being processed, we'll load up the next instruction. All right, so we're making the assumption, we're making an assumption that we will in fact be executing next instruction next, which is often going to be the case. If it turns out that we execute a jump, right, function call, loop, etc., then we'll just throw away the work we did on the next instruction and then resume with the fetched instruction. So in the unhappy case, we're no worse off than we were before, where we weren't bothering to do anything while the first instruction is being evaluated. In the happy case, after the first instruction is completed, we're already in process or possibly completed the next instruction if it takes fewer steps in the CPU to get through. All right, so on the test, I'm not going to ask you about how pipelining works. Pipelining is simply just like caching. Caching and pipelining are two areas where locality reference are patterns that we make use of because of phenomena. I don't think phenomena are a word, but the phenomenon of locality reference. It's just one of those things. It's a circumstance that exists, and we want to leverage the fact to make use of when we're developing the system. Other area. Fix my window size here so I have to keep scrolling the screen up. All right, temporal locality. Reference. This one's a resource recently used, is more likely to be used again soon than a resource that wasn't recently used. And so going back to the L1 through L3 cache, RAM, and possibly virtual memory. See, we have an application or applications in memory. And we want to perform some work. Right, so if we have a 4 GB system, but we need 6 GB of memory to have all of the applications loaded up to run. We'll use virtual memory, cover that 2 GB gap. And it's a virtual memory, virtual is just RAM being extended onto the hard disk. What the OS will do is move applications or part of applications that are under low utilization at the moment off RAM and onto disk. Once we're into RAM, same thing for what is going to be kept in L3 cache. All right, so L3 cache being down in the megabyte range, low megabyte range, can't have all of our applications. Data is sitting in there, so we'll have just pieces of one or more applications sitting there, and areas that are hot, meaning we have a lot of activity, are things that are going, that we want, are things that we want to be kept in L3 cache or higher, as opposed to data elements that have not been hit in a while. All right, so pages of data will be moving on and off the CPU memory in the algorithm, deciding who stays and who goes is going to leverage things like hit counts and how long ago things were hit. Right, so a hit is a resource being requested. Right, so like I in our loop, it's going to get a high hit count. Just like sum, right? So we'll presume all of those local variables made it onto the page on initial load up as the nanoseconds fly by. We may lose X in name from the cache since they have a low hit count inside the application execution. All right, so as the resources are requested, X and sum may have been kicked out. So when we do need them, next, we'll have to go to a slower memory and refetch that data. All right, so let's see. RAM speed, what kind of right, millions of seconds, so that's what, thousands, milliseconds, microseconds. I think that's about, sounds about right. Right, so RAM tends to be in the microsecond range, if not sub-microsecond range. When we talk about disk speeds, disk seek speed, here we tend to be in the millisecond type range. Right, high-end server drives, 4 milliseconds, right? 12 milliseconds being common for whatever's in your computer or laptop. The difference with the question is with the M1C max, everything is always loaded in cache. I don't know what an M1C max is. That's M1C max. Apple M1 chip, ARM-based chip instead of Intel. So what's the M1 chip? Let's see. System on a chip, integrated system components, CPU, GPU, RAM. Okay. CGR, that's yeah, right. So basically they're cramming a whole bunch of good stuff all down onto diecast, whatever you want to call it. Yeah, it is saying it's ARM based. I my hardware knowledge is moderate. When it comes time to we need a new computer is needed, I'll start doing my research, learn what the new now we're on DRAMs or whatever RAMs chips styles we're on at that point in time, and then educate myself, and then I'll build the machine. But in the years that come in between, it tends to fall out of sync for what's all the good. Yeah, like right, if you look at a typical, let's go back to Newegg. Look at a standard motherboard. Black Friday starts now. All right. I want Black Friday. I want change the website site since I've been here. All right. Fine. Search for motherboards. There we go. $74. Goodbye. All right. So, right. So right there we go. Right in the middle. There's where our CPU goes. So we'll put our memory chip there. Then we've got then we've got our two RAM slots over here. So it looks like a DDR4 RAM sockets way over here, right? Way it's what 30 millimeters away from the CPU. Right. So the signals have to travel that distance. Right. So here's the where's my annotation skills and skills. Yeah. Right. So here we have bad color. Let's try this color. All right. Here's our CPU socket. Our CPU is drop over there, but then here we have our memory over here. So there's going to be a bus that connects these that the data is going to have to go across to get things. So physical distance translates into time. Right? And if we've got we have our video card attached over here, right? Typically we want our video card on the slot that is closest to the CPU, because again, right, there's going to be that data bus that's connecting it to the CPU, and the greater the distance between these two components on the system, then the slower things are going to be. Right? So you want whatever you want your Bluetooth or something like that way over here if you have a plug-in card for your Bluetooth, because right, Bluetooth devices don't tend to need a great deal of high performance tech to get them to do their stuff. In fact, the whole concept of Bluetooth is it's simple, low grade, low power tech that it's just good enough for low data requirements, things like that, in short range. And of course, you have all your external devices here, right? So where is the disk? There's the disk, right? So he's got one of these. What's that format called? M1 spacing, right? It looks like a memory stick. I remember the first time I saw this, I was like, what the heck? Yeah, so it's a solid state, but it's like the M1 format. I forget what it's called. What's it called? It's stop annotating. Stop annotating. Stop annotating. All right. What is it? M2. That's more like it. I believe that's what we're looking at. Yeah, so let's clear my drawings. That's good enough. There we go, M2s. All right, it's crazy how small these things are. They're basically the size of a RAM stick, right? But by being small, it's got the extra advantage of being able to get closer to, right? So it's not a regular solid state disk or a normal spinning disk where you've got a cable connecting. When was my last build? Like 3 years ago. 2 years ago. It does have an M2 on it, so it hasn't been too terribly long. 3 years ago, I think. It's got 48 gigs of RAM on it. It's supposed to be 64, but one of the sticks decided not to work, and they only sell them in pairs, and forget about. Oh no, it's not overkill RAM. When you got, I run BlueStacks, and when you got 5, 10, 20 instances of BlueStacks up and running, and each one of these things wanting 1 or 2 gigs of RAM, it very, very quickly sucks up your RAM. Yeah, so my bottleneck on that one is CPU, right? Because I'll have each instance wants to use like 10% of the CPU, 8 to 12% of the CPU. 48 gigs. I get 4 16 gig sticks in there, and 3 of the sticks work. So, you know, one's not working in the fun. The CPU, you might want to go to water cooling then, because then you can move some of that bulk to a different area of your case. But I don't. Whenever I'm building a computer, I'm not doing top of the line stuff. I'm like doing, okay, what's last year's hot stuff? Because last year's hot stuff is half as expensive as this year's hot stuff, if not 2 years ago, right? Because and let's look at. We'll ignore GPUs because GPUs are just crazy for prices. But let's see. I did do an AM. I don't want motherboard. I want okay. Automated parts. Okay. What's going on here? I did do an AMD for my most recent build. I've done both Intel and AMD. There we go. Desktop processors. And let's see. Let's just go with that and sort by. $6,000 for, yeah. So I tend to go 1/10 of the price range of whatever the hot new crazy stuff is. Yeah, I mean, the mining has put a major shortage on the GPUs, and then just COVID's put a major shortage on a lot of other components. So I don't know if this is just because it's that top of the line or just because of the market volatility. Anyways, you just grab something, get the benchmark, and then scroll down a little while. CPU benchmark, that's a good website. Right, you just see where it's going to give it some sort of numbering where this thing is on the rating. And they should probably have a nice table. Shows you where this thing is on that table, and then I just basically scroll down big time. Yeah, there's only so much performance per buck I'm willing to pay, because by the time you finish building your machine, the device might be 20 or 30% lower than when it was when you got it. It's sold out on you know, the Black Friday sales. If you're planning on building, now's the time to try to grab up your hardware. 7,000 Chrome tabs open. Yeah, I tend to have a good number of Chrome tabs open myself. Start up a thread, get halfway through it, and something else comes up. And yeah, keep on spinning and eventually get back to it. Find out I've got 5 tabs of the same thing open because I had to spin back on new tabs. Anyways, we digress a little bit too far. All right, so there's going to be a paging going on in there. And of course, the more hardware you have, then the greater number of processes you can run, or the faster any given process is going to run through the system. Let's see. Yeah, that's good for that one. Now, what's next? We're talking about memory fragmentation. What was the other thing you mentioned? I wanted to talk about tonight. Yeah, memory fragmentation. Okay, dynamic memory caching. All right, so memory fragmentation. Okay, so memory can become fragmented over time. There are 3 different ways that the data that our memory can become fragmented. First, fragmentation, it doesn't even require any time. Is internal fragmentation. Fragmentation. Second type is external fragmentation. And lastly, we have data fragmentation. All right, so internal fragmentation. This is data space being wasted just through usage of data structures. All right, so going down to something such as a Boolean. Say we have this code, int, all right, is even. Number, and we have bool is even equals false, and then we say is even equals number modulo 2. Well, let's not do it math way. Right, if number modulo 2 is equal to 0, is even equals true, and then we can return is even. All right, simple function. Obviously not worthy of being a function, but we have a variable is even. Is even needs all of a single bit to track its state. However, being a stacked variable, and presumably in a 32-bit system, that variable is going to be taking that full word size of 32 bits of space on the stack. Thus, we have wasted 31 bits of memory. So we have 31 bits of internal fragmentation on that variable. Right. To a lesser extent, we also have that with number, unless we're actually using a value that's using the full range of number, right? Plus or minus 2 billion. Then all the significant bits are going to be zeros for a good number. Right, so right. Right, so for example, if the number is 31,110, whatever. And there are about 15 bits that are all zeros, not contributing to the actual state of the number. Right, so it's just more space was allocated for the data than we're actually using. Structures will also see this. Internal fragmentation. As it also wants things to line up on the word boundaries. And so let's do an example of that. Okay. Class struct doesn't really matter. Let's do a struct because keep it simple. Struct fragmentation. Int x and short y. Let's fragmentation 1. And let's go ahead and spit that out, make sure things are working. Okay, run and run, run. Let's see what bugs I have. 18. That's interesting. That's curious. How big are things here? Let's get a baseline here. Int. I mean, this is going to be dependent on the system we're running on. So if you run this on a different online compiler, you might get different numbers, but that part we don't care about what the actual number is, but we do care about the sizing of things. Oh, 8. Okay, that makes more sense. That was one from my name of, okay. All right, now I unconfused myself on an 18. That wasn't actually an 18, but rather an 8. And as you can see, our size are short. Should be a 2, but let's see. All right, there we go, 2. So I have an int, should take 4 bytes. I have a short, should take 2 bytes, but when I ask it how much memory a fragmentation variable takes, it comes along and says 8. So somehow 4 plus 2 equals 8. Right, so obviously that's mathematically not what the math is, but it's just how much space we're going to need for the structures, right? So this type is going to be wasting 2 bytes of space. It's going to end up being basically padding inside the structure, and we can see the same thing happen as we work with other types, and things can get even worse as we do additional things. Yeah, copy them both. X1, Y1, this is now fragmentation 2. This time we'll be wasting quite a bit more space. And part of that's going to be because of the way I decided to arrange things. Let's see. Let's go ahead and just go for Boolean. So I'm trying to use the wrong programming language. Try again. All right, so add our bool. Let's put these in size order. Boolean really should take 1 bit. Might even be taking 1 byte here. We'll see in a second. Scrolling. All right, so we're saying 1 byte for a bool inside the system. So we have 4 plus 1 plus 4 plus 1 should be 10, but our actual space allocation for fragmentation 2 is 16. And that's because I laid this out poorly. We can lay this out in a better way by just moving our ints together, our bools together, however way you want to look at that. So I have literally the exact same. I was wasting 6 bytes. It's the exact same structure in terms of the fields that it contains, 2 integers and 2 booleans. But this time it runs. Okay, I'll try again. All right, 2 has 16 like before, now 3 has 12. So what the system does when it does layout, where in memory these booleans are going to line up, it allows them to go not on the word boundary. So we can eke some additional space out of this. Let's see how much space we can eke out. Is it really 1 byte, or is it going to be doing, it probably is. Still doing 1 byte inside the struct. But here we were only wasting 2 bytes. That's an improvement. And then we'll have fragmentation 4. Let's see what that's going to give us, right? So the raw space actually needed, we have 6 booleans. So that's 6 plus 2 for our ints for 8. So 14 bytes if we're giving 1 byte per boolean. So 16 should be what we see here, right? So it gives us 16. So we're still wasting 2 bytes, but we did pack in quite a bit more of state that we can track inside this. Right? If space is really, really critical, you can do some bitwise type things where we actually do some bit mappings. We actually leverage every single bit that's in here and get the maximum amount of data utilization out of the space that we're allocating to that variable structure. Okay, so that's our internal fragmentation. And it's internal fragmentation. It's memory that have a hard time to try to reclaim. And in fact, these were just in memory operations. Let's do some data. All right. So we have this small text file. Here, even on disk, we're going to have fragmentation. It needs to be a lot more memory. Right, and what's the line me right now? Saying perhaps it's not actually on disk at the moment. I have to go find an existing text file because it's being a liar. Or it's not actually on disk yet. It's still just sitting in memory waiting to be written. All right, so this file is saying it's only 9 bytes in size. And let me see what happens if I go close it over here. Get it to persist. See, this is the problem with caching. This might be just the cache information, and it's not. So Notepad++. Let's add some more data to it. See if we can get this to give me real information. There we go, size on disk. So I've got up to 1,000 bytes in here. But the size on disk is 4,000 bytes, 4096. We're wasting 3K of disk space for this little file. And we're gonna have a hard time getting back. This is very often when you download installers, right? It's one exe, MSI, zip, or whatever it is, possibly a couple of cab files, where all those files are a bunch of compressed files where they've basically turned it into a each of those little files have internal fragmentation, causing the actual footprint on disk to be much larger than what it was that we had to install. Right? And I'm not counting you download some installer and that installer just goes in it and grabs all the data and then downloads it. I'm talking about everything that was downloaded, then it gets decompressed and laid out, folder structures, files, all that fun stuff, taking a big old footprint. Oh, your internet's unstable. That's hopefully the recording's going well. We'll find out later, I suppose. Right, so do we have any volunteers for a secondary recorder? I don't think I can give the ball to more than one person and try if someone else wants to jump on the train. Yeah, I don't know. I don't think I've ever had anyone through Zoom recording twice. I've had multiple people recording because they're using client-side software to record what's coming through on their side. I'm not seeing anyone pop up. To try to record. Okay, until it happens, we'll carry on. External fragmentation. These are empty spots in memory between allocated objects. All right, let's see. I can scroll. All right, I also give both of you the option. We'll see what happens. Okay, So we have 3 people. In theory, we might have the ball. We'll see. And it still says the recording's on. I don't know what kind of server backing support it might have for that to help rough out any gaps or holes that might occur. Okay. All right, so this type of fragmentation typically results as time goes by. And so for example, say we've created the objects A, B, C, D, E, and F. Then at some point, B and E are reclaimed. Right, either by a garbage collector or a manual delete command. So we have and enough. All right, so we'll have these objects take varying amounts of space. And oops. All right, so that's our initial space of memory that's being allocated for the various objects. Right, it might be a link node, an array, whatever it is, and then B and E later. B and E are deallocated, creating a space between A and C and D and F. Right, so those are memory fragments. They are available for use, but may be too small for the next allocation. All right, so the spaces in memory are between other allocated spaces of memory. File system, see the same type of thing as files get created and destroyed. The disk can build up. External fragmentation. External fragmentation can be addressed. We can compact the empty spaces together, forming larger blocks of available memory. All right, so some garbage collectors may do this as a part of their process. Yeah, so we're kind of there. It does need to be careful with how it does this, as the objects may be referred to from other places. So those references would need to be updated if they are moved around. All right, so say we're going to do the compaction. It's just going to do a straight compaction. Where C moves over. D overwrites some of the space that C previously was occupying. And then F slides over there. And now we have our external fragmentation has been eliminated. So if A has a reference to F, that reference needed to be updated to reflect F's new location in memory. All right, we're going to look at memory allocation strategies after this one. But the idea of doing the compaction is to help improve performance of other operations that are going to be happening in our system. And this leads us to our data fragmentation. Here, we have related pieces of data that are separated in memory. So continuing with before, if A does have a reference to F and other objects are unrelated, then there is a big gap between A and F. Consequence of that is that we'll not get to enjoy as much of a benefit that locality of reference would afford us had they been closer together. Right, so linked data structures can often suffer from data fragmentation, where the nodes in a linked list, for example, are not contiguously allocated in memory. All right, so let's say our list is A, B, C, and D, and let's say we also have some other tree memory. That's going to be P, Q, R, S, T. Our data may look like the following. All right, where we have A memory, and then P got created, and then B got created. We'll have two of them close together because we can, but then Q and R were created, then D hops along, and then we have S and T. All right, so our A, let's see, so we have our one list, A, B, C, and D. All related pieces of data, but there are gaps between, right? P, Q, and R are getting in the way. So when we do a page, say we start processing our linked list, the page of memory that it might grab in anticipation that P and B might be relevant would be this 6 chunks of memory. So as H starts to iterate through the list, all right, P ended up being data that we didn't need, but then B was grabbed. So getting to B ended up being very quickly because that in-memory navigation was at the lower levels of the hardware. But then when B wants to go to C, we didn't actually have C in that cache, so then grabs another page. Let's say grab C, Q, and R. So we get to C, but then we grab data that had nothing to do with it. So our fetch didn't work, and then we have to fetch again. We grab these 6 chunks. So the data fragmentation is going to give us problems. And this data fragmentation could be a byproduct of just the timing that objects were created, or it could have been something because the object is a long-lived object and memory has come and gone in the time where things left memory and new things got created. So a extremely intelligent garbage collector that actually understands the data models could attempt to deal with this data fragmentation. I don't know that there actually are any out there that do that, but by doing so, we'll gain some benefits of it moving things around. This is also one of the reasons I think the internal implementation of vector in the standard library, it's actually basically like array chunks. And then as it needs more memory, it just creates another array chunk and then does a linked list between those chunks. Because arrays are contiguously allocated, so if I create an array chunk of 16 elements or something like that, working through those 16 elements will be really quickly. And then when I try to get to the 17th element, then there's a memory navigation that has to happen there to get there. But then we managed to track all our benefits of random access and all fun stuff. But there's a bunch of extra overhead in terms of programmatic code has to be done to manage all that stuff. So try to leverage performance gains based off of locality of reference patterns, right? So we know that the system is going to try to fetch chunks of memory. We know how things are going to work. So when we design that code, we want to try to leverage those things so that our structure is the best that it can be type thing. All right. It pretty much covers our memory fragmentation. You talk some more about which data structures are likely to suffer from which types of fragmentation. But for now, let's go ahead and take a 10-minute break. 10 minutes. And we can carry on. So we can go on mute and away from the screen for a few minutes. All right. Memory allocation. All right, so specifically, dynamically allocated memory on the heap whenever a new keyword needs to be processed. You need to find an available spot on the heap, reserve that memory for the object being created, and then return back where in memory the object lives. Right, and then of course there's constructor logic and other things like that that are not relevant to this part. There are 3 common strategies. No, I mean, sound check. People can hear me, right?
Yes.
All right. Let's get 3 common strategies. We have best fit, worst fit, and first fit. First fit, we'll go through the available list and choose the first available chunk of memory that is large enough to service the request. Best fit, so that's in a nutshell. We'll get examples in a minute. Best fit goes through the available list. Available list and chooses area where the chunk of memory closest in size and large enough to fulfill the request. Fulfill the request, kind of like Price is Right bidding. No, actually, they're in the reverse. So never mind. That's the reverse. I will leave that to the side. Okay. And then worst fit uses the largest available chunk and allocates the memory there. Okay, so initially, memory or available memory is a single chunk. Say we have 1 megabyte chunk of memory that's allocated for heap space. All 3 approaches start out the same, as there is just 1 chunk to choose from. But as external fragmentation comes to bear, the list of available locations or chunks of available chunks of memory starts to grow. And we have this decisioning to be done there. So let's say example list. I've got 100, 40, 280, and I'll do another 100. That's fine. And then just use a dot 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 to represent the big chunk of memory. if we have a first fit request for 80 bytes. And the possible locations that could be used are 100, 200, 80, 100, and then we'll use that, creating a 20 unit space. So the resulting list should be the same numbers, except that first number becomes a 20. All right, so if we look at instead a best fit request, for the same size, with the same possible locations, all right, 100, 200, 80, 100, any of those can be used since the 80 is closest in size and large enough. We'll use it. Happens also be a perfect allocation. So the available list, also known as the free list, available list will shrink down by 1. So our resulting available list and for the 200, it goes away, and then the big chunk at the end. Right, same thing, we know worst fit. Same thing with this approach, we only track the large chunk of memory. So we'll use that ellipse space and it just becomes smaller. So the resulting list is the same as the initial list. Since I don't have an actual number on that final space, it will look the same. Okay, so these different strategies are going to require different approaches and data structures to maintain the data so that we can work with what we're doing here. Some of them, they have their advantages and disadvantages. All right, so first fit. Disadvantage here. Advantage here is just iterating down a list, iterating. Which memory? It took the big chunk at the end. All right, so it's in that. Let's do the high color. It took up that space. So that space is now 80 smaller than it was before. So if it was 20,000, now it's 19,920 type thing. Yeah, it could be in kilobytes. It's just an arbitrary unit of measure. It could be kilobytes, it could be bytes. Right? It just depends on the objects that we're allocating. Right? If I'm creating 100 byte arrays, 40 byte arrays, or 40 kilobyte, bytes would be the better representation because our objects, just like we had over here, right, if I come along and I say new fragmentation type thing, right? It's going to be however many bytes that the program said we needed for that. So usually memory allocations are going to be in bytes, but if we ask for an array, right, 1,000 element array, then we're looking at least 1,000 bytes, which is the smallest type being a byte per element, and more likely 4 kilobytes in space because we're probably using 4 bytes per element more often than not. Many of our integral data types are 4 bytes. Then, of course, all our reference types are 4 bytes, assuming, again, 32-bit system. All right, so the first fit, we're just iterating the list as it is, so we may need to iterate a good long list. Of course, we can maintain the data in a fashion that has some order so that we can improve the situation, but we're less likely to remove an item from the list with this approach. All right, so one way to address this, data is with a sorted array. Then we can quick sort our way. Quick sort, sorry, get my brain all messed up. Binary search. Our way to the first chunk that is large enough. And then make use of that space. Which does mean we'll be reducing size of that chunk. And then we would have to rearrange values. All right. Of course, you can also look at heaps, skip lists, etc. to track the data. Sometimes we'll even create and maintain multiple lists based on the size of the chunks. We have small allocations, medium, and large. That can help rein in chaos with the amount of available spaces starts to grow large. And as applications start living longer and longer and longer, or you have a service application, you got an operating system, whatever, things that are around for minutes to hours to days, things tend to come and go quite frequently. If you're using an object-oriented language, right, with heap allocations, right, if you're using still a structured language with heap allocations, it's still the same thing, but you tend to have a little bit less emphasis on objects with like C than you would with C++ or C# or Java or some purely object-oriented language where everything's an object. as our starting point. So it just depends on various things. And sometimes we'll get into a situation where our chunks of memory are just so small that they've become unusable. And that is one of the problems that best fit can run into. Disadvantage here is if we have, for example, a space that is closest at 100, and we need to allocate 90. That leaves us, say, 10 unit space, which may be unusable in our system. So that can be a bit problematic, as well as we start to accrue large number of tiny chunks of memory floating around. Our worst fit disadvantage here is, since we're always taking from the largest chunk, can run into a situation where we have, say, 200 kilobytes of space available. The largest chunk is, let's say it's 4 kilobytes, and we want to create an object that is 6 kilobytes. Something that we should be able to do, but we don't have a big chunk available to us. Right, so worst fit has the advantage of being very quick because we just track, basically, right? Here, for worst fit, just keep a max heap. And the largest chunk is at the top. And as we eat away at it, it tends to stay at the top. So getting to that chunk is big O1. And since it stays, maintaining structure also stays a big O1 for allocations. As deallocations come along, then those smaller entries find their way deeper into the tree. All right, so the different memory strategies have their pluses and minuses, and of course, these are just the general approaches. The way the actual implementation of the dynamic memory allocation that is used could, of course, use a hybrid of these. All right, we might have worst fit running for a while, but then which means we just keep using that same big chunk as they're all going to do to start. And as deallocations come along, we might look at opportunities. Do we have any perfect fits? All right, there's 128 byte memory requests and I have 128 byte space available. So we can go ahead and just jump to it and grab it and then pull it out of the available list, and then we're good to go. We just need to pay attention to, what our costs are going to be, what structures are going to help aid us in working with this data, because if we're adding items to a list and we're removing items to the list, and do we need to maintain any ordering on the list? All that fun stuff needs to be accounted for, so we can look at the costs and benefits of one structure versus another for these various operations. That somewhat makes sense.
Yeah.
All right, let's see, almost 8 o'clock. Yeah, for our garbage collection, I think I'll just go ahead and offline make some more examples for that, and I'll throw them on Canvas. People can check those out as we go along. Otherwise, I think that's a good place to stop with this being Thanksgiving week for lecture materials. So that just leaves talking about program 4. So what questions do we have about program 4 at the moment? We have a couple have turned it in already. Scope tracking, okay. Let's see, which account am I using here? All right, so scope. All right, so what we want to do for scope, or there's several ways you can go about this. One way to do this is you add scope to your variable class. And what we'll do here inside main, just say scope equals 1 to start. So when we get to a start block, we can go ahead, don't have much to do here other than to increase the scope. So when we go ahead and add our variables, I'll pass scope along here. Table add, int scope. That scope equals scope. So we can track the scope as they're added to it. And when we get to a finished block, here what we want to do is go ahead and do a destroy and pass along the scope, and then decrement the scope. And the idea of what the table is going to do here is find all the variables that belong to that scope and kill them. So for each list in the table, tell that list to remove variables that have the specified scope. And the other approach people will do is they'll do, instead of a single chain hash table, they'll do, right, an array of chain hash tables. In which case here, what we'll do is they'll say increase the scope, and they'll just say my table array of said scope equals a new chained hash table. And instead of saying a table to destroy, we'll just say table array of our old scope, right, equals null type thing. We just kill it. And so when we do the scope resolution Well, you definitely need to change it into C++ to submit, right? So when you're doing scope resolution, right? So let's assuming we do have the one chain table. So when we're adding my annotation, so I can draw here. Okay. Right. So let's try to add in some boxes. So we just have 3 lists, right? 0, 1, and 2. And let's say at some point in time we had the variable, right, x, which is presently the value 5 and is defined at scope 1. And let's say we go ahead and create another variable x down the line. X value 22 and has scope 2. Right, so when I add variables to our list, I just do a push to head or add to head pattern. That way variables that are higher in scope or closer in scope, however you want to look at that, are further to the left in the list. So if we come along and say, right, print x, this is going to output our 22 because it comes into the list, finds x, that's x goes to list 0, comes in here and sees we have x as the name of the variable. It found it, it returns the 22 back, and it prints it out. Right, so this is, so let's say we had var x equals 5, then we had a start, and var x equals 22. And then we say print x, this outputs 22, and then we have a finish. We say print x, this outputs a 5. Right, so when we hit this finish blocks, that is going to kill this scope 2 variable. So when we come along to print x down here after this finish, we hash it, find that it goes to list 0. Right, went to list 0. For the first element, happens to be an x, right? The key matches, and we spit out 5, right? Say z also ends up in the list. We can make sure we differentiate between x and z. Do always need to double check the key when we're doing a lookup because collisions happen, especially if you have just a 3-list table. Right, so right, tweak this code, say insert at 0 and then the value type thing. So it pushes it all the way to the front. Presuming such a function exists, right? We would have to create that bit of logic ourselves. Again, I'm just generalizing things here. It's actually not like, does not contain, what is it called? I thought I had one. It's just insert. Okay. Get my languages confused. All right, so we're inserting to the beginning of the list so that when we do our lookup, it's already in the right order. The lookup is faster, right? So one of the reasons we do this is we want it to be faster to find who we're looking for, and it also handles our scope resolution for us in the way that we want it to. Right, so if you're doing it with the multiple lists approach, then you have to work your way backwards. So when we're doing our print, we got to look at table scope. Does the current scope table have X defined in it? If it does, okay, we'll use it. If it does not, then I need to go down. Let's say we have 3 scopes. So I'm at scope 2. Does scope 2 have X? If it does, we're done. Print out. If it doesn't, then I go to scope 1. Do you have X? No. It's scope 0. You have X? Yes or no? If you do, we print out. If it's no, then we say, oh, this variable is undefined. I don't know who you're talking about. I can't print something that we haven't previously defined. Right, and either approach is fine. So a little bit, second approach is a little bit heavier because you're creating a whole table and you're deleting a whole table every time you enter and leave a scope, but the maintenance of the structure is simpler that way. It's just saying table goes away. You don't have to add a bunch of code to the list class to have the delete logic for variables because we're only deleting variables when they fall out of scope. So by having the whole table go out of scope, and so either approach is fine. I don't particularly care what approach you use. The key is you're using a chained hash table for our collision resolution. You're handling the keywords of the language. Your variables are getting stored into your table. You can load them up. Right? The extra credit, you just need to message me that to me directly what is you want to add as a language feature for the extra credit. We have a couple people doing a couple things. So the list of available options is diminishing because it is a unique constraint for that extra credit. Right? Ifs and switches have already been claimed. So for looping, while looping, functions, whatever language feature you might want to add that doesn't already have. Yeah, you just message me in Canvas or Zoom or whatever. Email, doesn't matter. Oh, it's at most 10% of the grade of the assignment grade. If you want to, yeah, you always message me if you change things. Yep, that works, Arthur. So looks like if statements are available again. Just make sure you call that out when you submit it so I can explicitly look for it. Because I don't explicitly look for it because very few people tend to attempt it. Let's see, did I fix my bugs in my sample code? Name table array. Yes, indeed. Let's be comment out because that does not exist. Okay. Yeah, that should be fine, Malik. You just need to message me in Canvas because I have a record because the chat in Zoom is not something that I hold on to. It's not an extra credit assignment. It's a feature of program 4 that you do extra credit. Yes, it's an array of linked lists. So you can grab your adjacency list code for that exercise we did, I guess 3 weeks ago now, and it's basically that code. You just need to rename things plus add some functionality to support the variables and the actions that we want to do for those. I would use a small size for the hash table. 3 is perfectly good because that way you can make sure your collision handling is correct because my test programs are definitely going to be forcing the issue of causing collisions. And if I say to print X and you print the value of Y because you don't have 3 as a prime number, it's a very small prime number, but it is a prime number. Right, so you gotta make sure your scope resolution is good. Right, the number of variables that we're gonna have in the table at any given time isn't gonna be a lot. So even with just 3 elements, each list might only have 2 or 3 elements long. So it wouldn't be too bad for the efficacy. Okay, syllabus. think we have 4 more classes, right? What do we have? We have 29th, 2, 3, and the final, right? So should be ready. Everything for test 5 at this point. Double check. It's possible next Monday we might do something else, but so I will get the practice test available. I might have it right before next time, but that is slated for December. And we will have test 5 on the week before the final. So the week before the final, there shouldn't be any new lecture material. It'll just be take test 5, go over test 5, and then any additional last items you want to talk about for the final exam. And then the day of the final exam, there's just the final exam. It is twice as long, so 2-hour and 10-minute window. So it takes up pretty much most of the class. And then if people stick around, we will be able to go over some of the final exam. Usually there tends to be more questions than there is time for it, so we won't get through everything. We'll see what we can get through. Yes, so the week before the final is test 5, going over the test, and then the final exam review. Remember, the final exam is cumulative. It's the entire semester. Back to our roots at functional and notation, stacks, queues, arrays, linear search, binary search, et cetera, all the way down to what we get through on December 6th. Yeah, so we have 2 more days of just full lecture. And then just wrapping up with the tests. Just the last program 4 due. And then we'll be done. Any other questions about anything else at the moment? Otherwise, I think we'll end it a little bit early tonight with last minute shopping that needs to be done. Yeah, you can always resubmit. If you lose points on a submission, other than for it being late, you can resubmit to get points back. If it's a late submission, you lost points for being late, then those points are lost. But if you lost points because you missed something or you did something incorrectly and I called it out, then you can resubmit and get partial credit back. Can I show the code? It's still the same link as we had last time. I just resaved it. I can go ahead and drop that in the chat again. Another question fly by. Let me see what it was. A couple questions. 1 second. Let's see. Yeah, if you want to create an array data type, that would be a language enhancement because right now the language does not support arrays. It just supports, floats, and that's it. Is now, yeah, it's still late, so you can't get full credit back after the fact, but you can basically get like half of it back for things that are wrong. Late penalty is not as stark as it is for an original submission. It's much better to turn in a mostly working submission on time, get half credit, 3/4 credit, and then fix whatever's wrong after the fact, and then get half of those points back as opposed to like wait a week to get it all there because points are eroding as time goes on. All right, happy Thanksgiving. Make sure you get your proper fill of tryptophan. Good proteins, bad proteins, everything in between. And we'll see you next week. Good night.